when we left off, right? I've explained this. I finished explaining this in the last video, so you can review the end of that or read it in the book if you like. Let's practice this a little bit. So we've got two different climates represented here. And at a glance, how I read this is a couple of things. I look across the bottom and I see, oh my gosh, look at all that black, hatch marks, black. That means that the average temperature from January probably through April is below freezing. For the rest of the summer, there's always a chance of freezing at some point in each of those months, and then we quickly return to a period where the average temperature is below zero. So I'm thinking, okay, this is pretty far north. On one side, and the amount of precipitation, I'm looking at this up here, I'm saying, wow, 282 millimeters, that's about 25 centimeters, it's 28 centimeters. That's not very much precipitation. In fact, 25 centimeters is kind of the cutoff for what we refer to as desert. On the other side, average annual temperature is almost minus 12 degrees Celsius. All right, so this is really freaking cold. I look across the top and I see all these vertical hatching all through here. So that's telling me that this precipitation is always enough for plant growth. See this temperature line way down here, that's the temperature. So it's so cold that you don't need a lot of water. See, that's the thing about these things, is that the amount of plants need is related to how hot it is. The hotter it is, the more water they need. So in this far northern tundra region, there's plenty of moisture for plant growth. The problem is the temperature. So that's how I read that graph. Let's go over here to Denver, Colorado, the mile-high city. What do I see? I see a lot of cold. I look across the top. I see, ooh, look at these precipitation temperature lines crossing at one point. Okay, that's telling me it's going to get really dry in the summers in Denver. It's also telling me that it might be a lot of fun to backpack because it's probably not going to get rained on. Might be hard to find water though. All right, so same thing, same rigmarole. We've got a lot of cold winters, just a little bit of few months in the summer where we don't expect any freezing to occur in Denver per se. You go up into the mountains from Denver, you're going to get below freezing at some point in the summer, but down in Denver, you're not going to get that. We have a total amount of precipitation of 357 millimeters, about 35 centimeters, a third of a meter about. Okay, that's about a third of what we get in Oxford. That's about a third of what we get in Oxford. Just keep that in mind when you think about the fires burning out west. So we have plenty of moisture throughout the spring, throughout the winter and spring, but we get rising temperatures and declining precipitation, so we have this summertime drought. Here we have Chicago. We already looked at Chicago. Here we have San Juan, Puerto Rico, where we've got 1.5 meters of annual precipitation, 1.5 meters of annual precipitation, and an average annual temperature of about 26 degrees Celsius. So we've got ample moisture throughout the year. We've got a little dip, and this is related to the rotation of the Earth and how the sun is heating the equator and other areas. We do have a little bit of a dry spell in around February, but still, it's still plenty of moisture. And we see, while we're on moisture, this black area at the top is just because these axes would have to go really, really high to capture all the moisture. So this is just saying it's in excess of the amount seen there. Characteristic of all tropical areas, we see temperature that does not vary hardly at all during the year. So the temperature always is hovering around 25 degrees C. That's because of the fact that the surface of the Earth is never far from perpendicular to the incoming radiation. That's really how we define the tropical and subtropical region by the amount of variation. In this case, the daily variation is greater than the annual variation. And of course, we don't see any frost throughout the year in San Juan. Here we have a couple other areas that are on fire right now. San Francisco we look at. We see at a glance that we don't expect precipitation in San Francisco, which is right on the water. And being on the water helps moderate the climate. Water, as this is described in the reading, but water, big bodies of water heat up and cool down very, very, very slowly. And so San Francisco, being right on the water, benefits from that. So it never gets too hot in the summer because the ocean is cooling the air relative to the landmass. You just go a few more miles inland from San Francisco and it can get very hot. But right on the water, it stays relatively cool in the summer. It also stays relatively warm in the winter because, again, the ocean just doesn't heat up and cool down very fast. The ocean temperature is fairly constant. What we see in the San Francisco graph is highly, highly characteristic of what's referred to as Mediterranean climates, where we have warm, moist winters, lots of precipitation in the winter, and very little in the summer. So we have, as you'll notice here, we have these hatched marks in areas with plenty of precipitation, but now where the precipitation line falls below the temperature line, we see a different patterning arise. And this patterning is telling us that there is a serious water deficit for plants. And these plants in these regions are adapted to this kind of climate. And there are many species that are endemic or native to, that is, they evolved there and they don't grow anywhere else. That is, they're adapted to these Mediterranean climates of moderate, moist winters and very dry summers. And that's common throughout the west coast of North America, at least below from San Francisco on south. Even as you go north from there, you still see a little bit of this pattern. It just tends to be not as extreme. And of course, we've got the desert of Phoenix, Arizona, where we see only a brief period during the winter where we have sufficient moisture, and then throughout most of the year we have severe drought conditions. We've got a little monsoon period in midsummer where we get big thunderstorms, and so we get a certain amount of rainfall in late summer, but mostly it's really just a serious dry period. All right, disturbance, and I'm going to talk more about this actually in the next set of slides, but I want to breeze through it. Disturbance is what ecologists call discrete events resulting in a big change to the environment and typically lots of mortality, lots of death. So a big change to the physical environment and often a lot of death. It is a natural phenomenon, and many organisms require these disturbances in order to reproduce and thrive. Chief among these is fire. Fire is a natural part of all ecosystems. It is very common in some ecosystems like grasslands and in shrublands that are common throughout our desert Southwest. It becomes increasingly uncommon as you move to cooler environments and more moist environments. But fire is a natural part of our environments. So disturbances, there are lots of others. Severe wind, severe snow, ice, landslides, volcanoes, and human disturbances can be characterized, all of these can be characterized by three factors. One being their intensity. That is, and we refer to intensity as how much change is happening per unit area. So in a square meter or in a square mile, how much damage is done, how much mortality is there, and how much physical change is there caused by, say, an ice storm or a landslide or a volcano or etc. So this is sort of the amount of change per, square mile or square kilometer, whatever. The other thing is frequency, how often these disturbances come through. In some areas, like some grasslands, fires are expected every year, every couple of years. We expect fire to be very, very common and happen quite frequently. In other areas, like the boreal forest way up north, we expect fire, but only very rarely. And so frequency is an important part of any disturbance regime in an ecosystem. And the other is extent. Over what size area of an ecosystem or a landscape or a biome, how big of an area is affected. Consider a tree falling down in the forest, right? So a tree gets old, it's diseased, it dies, it falls over. That's a disturbance to that particular little location. That's a disturbance. But if you step way back and look at the forest as a whole, it's a normal part of the ongoing life and death of individuals in that forest. If you step back, far at all. But in that tree fall gap, that tree has died and radically changed the light regime and the soil moisture and a lot of things in that one location. So we think of that as a very small disturbance. But to the forest as a whole, we wouldn't consider it a disturbance. So disturbances are always defined by their intensity, their frequency, and their extent. We'll talk a lot more about fire later, and so that's all. We'll just wrap this up for now and end this. And I'll see you in the next video.